my name is Bradley Grzesiak. You can find me on the internet as Listrophy and pretty much everywhere. I started a company with Steve Anderson over there called BendyWorks a few years back, and I run a infrequently updated blog called namingthingshard.com. So the talk in my title is better than ROT3, but it really should be called Don't Try This at Home. So a brief overview of what I'm going to talk about is a historical perspective of cryptography, symmetric encryption, modes of symmetric encryption, hashing, asymmetric encryption, signing, and then implications on how that affects Ruby. So we all know about ROT13. It's actually one instance of a class of algorithms called ROT-N, and it actually has the official title of the Caesar cipher. Apparently, Julius Caesar used this all the time to talk to his generals out in the field. The Caesar cipher, you encrypt by modular addition, you decrypt by modular subtraction, and the key, the thing you want to keep secret, is just n. So I'm going to have a bunch of diagrams throughout this presentation. I'm using a couple of features to help keep things straight. First thing is anything in uppercase is going to be public knowledge, something that you can let out into the world and not worry about it. I made it caps because it would be loud. Secret knowledge is going to be all in lowercase. Something that's in a box is an algorithm, and something in a circle is data. Don't mind the fact that that's not a circle. So ROT-N, you take your secret plain text, the thing you don't want anyone else to see except the intended recipient. You run it through the algorithm, ROT-N, which is public. You keep the key n secret, and then you come up with a ciphertext that you send on its way. And to decrypt, you use the inverse of ROT-N, which is modular subtraction. Again, you apply the secret n, and you get back the plain text. Not too difficult. The reason we like to make fun of ROT13 is because ROT13 is equivalent to inverse of ROT13. So hence the joke about double ROT13. Obviously, there are some serious vulnerabilities with this scheme. Brute force attack, you have 25 combinations to try. ROT0 isn't very effective, so you have 25 others to try. It only encrypts alphabetic stuff, which is usually a problem. So you can move on to something more advanced like the substitution cipher. You may have seen these in the Sunday newspaper. So basically, you take an alphabet and a scrambled alphabet and make a map between the two. You can extend that further, and instead of just doing the alphabet, you can use numbers, symbols, what have you. So this also has some vulnerabilities. You can use letter frequency analysis because E is the most frequent letter used in the English language. It might be a different letter in different languages, but in English it's E. You have word frequency analysis. So E and T are pretty common, and if you see a word that's encrypted that starts with a T, has a blank, has an E, you can assume with high probability that the middle letter is H. Might be O, but it's probably H. And there's also temporal analysis. So if you keep sending more or less the same message over and over, let's say at 8 a.m. you're reporting that the weather is fine or cloudy or whatever, something I'll use a little later as well, you can start using the time that the message is sent to help you in decrypting. So moving from a monograph where you have one letter to another letter, you can start using something called a digraph cipher. So Wheatstone invented this a cipher. It's not called the Wheatstone cipher, it's called the PLAYFAIR cipher. Wheatstone, you may have remembered his name from electrical engineering classes if you took any. He created something called the Wheatstone Bridge, kind of cool. He also invented a cipher, but Lord Playfair really liked it and told everyone about it, so it's named the PLAYFAIR cipher. So you use a passphrase as the key. So let's take correct horse battery stable. And if you read XKCD, you will recognize this from this particular comic. If you don't read XKCD, start doing so immediately. Go through all over 900 of the comics so far. It's well worth your time. But going back to the passphrase, what you do is you take the passphrase, and anytime a letter is repeated, you delete the non-first character. So for example, we're going to remove the second R incorrect, the O in horse because the O is incorrect, etc. And you come up with Koreth's Bapel. And so you arrange those into a 5x5 grid. So you can see CORET, and it keeps going. And then you get to the middle where you run out, and you just pad the rest of the 5x5 square with the remaining letters of the alphabet in order. And because it's 5x5, you have 25. There's 26 letters. You actually use I and J as the same. Or you can omit Q or whatever you want to do, but this is the general way it was used. So let's say we want to encrypt NP. So we take our square, we find N and P, kind of in the middle there, and then that forms a rectangle. And so we take that rectangle and find the other two corners of the rectangle, and that's your encrypted pair. So here we would output if. There are rules on what happens if they're in the same row, the same column, or two in a row. I won't go into those. Obviously, this also has some vulnerabilities, but it is better than substitution ciphering. It's susceptible to brute force. There are 600 digraph combinations, which is just 26 times 25. It has a poor padding scheme because in that 5x5 square, the bottom right is almost always Z unless Z appears in your passphrase. It's not very good for security. It's alphabetical only, again. So this is a problem that the Germans faced, actually, in World War II with their Enigma machine. The Enigma machine only encrypted letters. And so there was a common report that would be sent with a number from 1 to 12 that starts off the message. They couldn't encrypt numbers, so they spelled it out. And the spelled out words for the numbers 1 through 12 used almost all the letters in the English and German language. So if you assume that this message starts with a number that's spelled out, you have 12 possibilities, and you can go from there. Also, it suffers from digraph frequency analysis. So the letters DE and ED appear frequently. RE, ER also appear frequently. And so you can do the same thing with that you do with substitution ciphering with the letter E and T and so on. You can also use an XOR stream, go a little further. So if I want to encrypt the letters NP, I convert that to ASCII, a bunch of bits. I'm going to come up with a random key called just P star. And if I XOR all those bits together, I get greater than Z. I chose values that resulted in ASCII characters, but they don't have to be. They can certainly be non-printing characters. This also has some vulnerabilities. First and foremost, if you know two of the things, you can always get the third. So let's say you have a ciphertext and you have the plain text. If you XOR those together, you get the key. And if the person you're attacking uses that key over and over again, then you can use that key and their ciphertext to always decrypt their ciphertext. There's also no diffusion. This is a topic I'm going to get into a little later. But the idea of diffusion is, or at least the absence of diffusion in XOR, is that a bit in position A in the plain text only affects the bit in position A in the ciphertext. It doesn't affect other bits in the result. But XOR can be used very effectively in the idea of a one-time pad. So one-time pad is where you have a key that is as long as the message that you're sending, and it is never repeated. Mathematically, this is unbreakable. But it's never used because if you're encrypting a 1 megabyte file, you have to have a key that's 1 megabyte long, and you can never reuse it. And somehow you have to get that key to the next person. So not exactly used very frequently. So let's talk about real symmetric cryptography. So the first concept is confusion. This is the substitution of bits, like the substitution cipher. 1 byte corresponds to another byte. You have diffusion, where if you change one bit in the plain text, it affects many, many, many bits in the ciphertext. So the ideal situation is that if you change 1 bit in the plain text, every bit in the ciphertext has a 50% probability of changing. Another important idea is that you have a public algorithm and a secret key. So if you have a gun pointed to your head and the person says, how did you encrypt this? If it's some proprietary thing that once you tell someone how it works, they'll be able to decipher it, that's bad because then they can coerce you to say that. If instead you can say, I use this algorithm, read about it on Wikipedia, I don't know what the key is though, then you're, well, hopefully they don't blow your brains out. And the other thing about real symmetric cryptography is that it tends to operate on a single block size. So you can only encrypt 64 bits into another 64 bits, or 128 bits into another 128 bits. There are things you can do to make that apply to an arbitrary size message. So this is the algorithm. You get plain text, you put it through a symmetric algorithm with a key, and you get ciphertext. The inverse is pretty basic as well. Flip the arrows, use the inverse of the symmetric algorithm, and this looks awfully familiar. The only difference is that ROT13 is very simple, and your typical symmetric algorithm is not. So a couple of examples of real symmetric encryption are Ds, 3Ds, AES, also known as Rindal. That is how you pronounce that word. Ds was published in 1977, and it was standardized in 1979. It uses a 56-bit key, a 64-bit block size, and triple Ds was introduced after that was determined that it wasn't enough. So that was published in 1998. Think about that. That was 13 years ago that we stopped kind of using a 56-bit key for pretty much anything. Generally it uses a 168-bit key, which is actually just three 56-bit keys next to each other. It also uses 64-bit block size, and the encryption algorithm is really simple. Use Ds just 3 times. Encrypt the plain text with the first third of the key, then decrypt at the second third, and then encrypt again with the third third. Simple as that. Moving on to AES. Before I actually get into that, I want you to mentally sign this agreement. I blank promise that once I see how simple AES really is, I will not implement it in production code, even though it would be really fun. This agreement shall be in effect until the undersigned creates a meaningful interpretive dance that compares and contrasts cache-based, timing, and other side channel attacks and their countermeasures. Implementing this stuff securely is incredibly difficult and is the topic of a lot of debate at all the graybeard cryptographic conferences. So don't implement this. Anyway, I have a QR code at the end of the presentation that has all my references. That image was taken from a great stick figure comic, not written by Randall Munroe, but Jeff Moser, that explains AES quite thoroughly. So AES was written by Vincent Ryman and Johan Dahmen, and they combined their last names into Rindal. It was published in '98 at the behest of the NIST, National Institute of Standards and something technology, maybe. And it was anointed as the winner of the AES encryption scheme in 2001. It used a 128-bit block, which is basically a 4x4 matrix of 8-bit characters. And it uses a 128, 192, or a 256-bit key. So it has a few vulnerabilities. They're not very big, and they generally refer to retrieving the key. So that means you're trying to get the key out, given that you already know both the ciphertext and the plaintext. So you're kind of broken already, but it's even though you have the ciphertext and the plaintext, it's really hard to get the key back, and there are a couple of vulnerabilities. The first is extended sparse linearization, XSL attack. It has a very high work factor, so that even though you can reduce the number of attacks that you do, the amount of work done per attack just gets so big that it's not really feasible anyway. There's the related key attacks on 256-bit AES, so you can kind of crack AES 256-bit through 9, 10, or 11 rounds, but the standard says 14 rounds, so you can't really use that. You have kind of a 3-round safety margin on that. There's bi-click analysis, which reduces the effectiveness of AES by a factor of 4. I have no idea what bi-clicks are, but the idea that you're reducing the effort by a factor of 4 makes no difference whatsoever, because the most effective attack on a brute force attack on cryptography has been by distributed.net, and it was a 64-bit key that was broken. And so when you're talking about 128 bits, every bit you add doubles the amount of effort. So to get from 64 to 128 isn't a doubling of effort, it's 2 to the 64 times the effort. And then there's also side channel attacks. If someone manages to get a computer running on your machine, first of all, you're kind of already screwed. But some very smart people have written software that lets them determine what your key is in as little as 800 operations or under 100 milliseconds. So make sure that your servers are secure. So the general operation is that you take a key, and it's also a round key. So in the first round, you basically take the key, and you XOR it with your message, that 4x4 matrix of characters. That applies confusion. Then you shift the rows of this matrix. That applies diffusion. You mix the columns, more diffusion. And then you do that 10, 12, or 14 times, depending on the length of your key. This is all you need to know. So memorize that, and you should be good. But remember, don't implement it, ever. So moving on to symmetric modes of encryption. Say you want to encrypt more than 16 bytes of information. This is how you use modes of encryption to do that. So if you were to open terminal and type OpenSSL space and then tab twice, you'll get that, which is a lot of stuff. It's all intermingled as well. There's symmetric, asymmetric, all kinds of stuff in there. If you pick one of those, let's say DES-EDE3, because that sounds familiar from earlier in the talk, and a -H, then you get all this stuff. So these are all symmetric ciphers with a bunch of modes on them. If we pick one at random and pick ECB, whatever, if you've done that, you just failed. OpenSSL doesn't tell you that this is a tremendously insecure way of encrypting things. It just says, here, try it. This is how ECB works. Looks pretty straightforward, right? You take your first plain text block of 128 bits, encrypt it into ciphertext. Second, 128 bits, encrypted into ciphertext. But it has a lot of vulnerabilities. You have information leakage and pattern analysis. So information leakage, again, if you're sending messages that say the weather is sunny, the weather is rainy, you end up, and you use some magic key that results in the output being 1 through 8, 1 through 8, 1 through 8. The messages look very much the same all the way up to that sunny or rainy. By doing that, you're leaking information. There's also pattern analysis problems. This image of tux is encrypted with ECB. If you're really trying to hide something, this doesn't look very hidden. So don't use ECB. The solution would be to use something like chain block cipher. So basically, the idea is that every block depends on the previous block, and the first block depends on an initialization vector, which you can make public. That's why it's in caps. So this is the idea behind it. You take your first plain text block, XOR it with your initialization vector, run it through the algorithm, you get ciphertext 1, and you use ciphertext 1, XOR that with plain text 2, and keep going and keep going. So that's how chain block ciphering works. This is kind of an overview. There are many other ways that mix up the lines quite a bit more, but this works. So it has a few vulnerabilities that are all related to you sucking. So if you use the same initialization vector, you've just used ECB, except you're calling it CBC. Once again, we see the output at the beginning is 1 through 8, 1 through 8, 1 through 8. And at the bottom, it's 1 through 8, 1 through 8, and then gibberish, because it actually changed at that point. So the solution is you should never use the same initialization vector for the same key. And it's pretty much immune to pattern analysis. That's a pretty well-hidden tux. So the moral is don't actually drop down to this level, but if you have to, use AES 128, 192, 256, whatever, and use CBC mode. The next topic is hashing. Yeah?
What would you recommend you use if you have to write something that needs to be tolerant to failures of your blocks? So with CBC, if you've got a corrupt block in the middle, everything after is garbage.
The question was, what do you do about tolerance to corruption in the middle of the cipher? There are other ones, OFB, I can't remember the rest of them, but there are a number that are more tolerant to that. They kind of reset themselves every few blocks. Check out Wikipedia. It's got a lot of information actually on Wikipedia. So hashes, we've heard about these: MD5, SHA, bcrypt. If you're hashing passwords, please use bcrypt. There's also HMAC, which you use SHA or MD5 with HMAC. And I'll go through each one of those. Traditional hashes, MD5, SHA-1, are designed to be fast. They're designed to take a large amount of information and crush it down into a small string that you can compare to detect if like one bit has changed in the giant amount of information. But that, in effect, provides very little security, if any, against brute force. Computers are getting fast enough that you can just brute force everything. And salt doesn't help. If you don't solve things, yes, you're vulnerable to rainbow tables, but rainbow tables isn't brute force. You can just use the salt and then brute force against the salt and all your guesses for the password. And yeah, if you're using a fast algorithm like MD5 or SHA, you're helping out the attackers. So this is how a traditional hash works. You throw some plain text into an algorithm, and instead of outputting the result of the algorithm, you just feed that into the next block and keep going until you get the final value and you output the hash. So it's basically symmetric encryption, but you don't output anything except for the very last thing. bcrypt is similar. It uses an initialization vector. That's why if you ever use bcrypt and you encrypt the same thing twice, it will actually be something different because it's using an initialization vector. So you can't actually compare the output of bcrypt to see if the encrypted contents are the same. So use an initialization vector, and then it uses this public value called n, which is basically a work factor that says, if I am using 10 as my n right now, if I bump that to 11, then the algorithm will take twice as long. And so this is very resistant to computers getting faster over time. And so over time, you can just say, well, computers got faster after 18 months. Let's bump up n. And so it's pretty effective for that kind of thing. N, IV, and the hash are all public information. And you can go one step further and have authentication code that are usually tied to a hash. And it's basically the same thing, but you pass in a secret key. And this is more used in things like asymmetric signing, which I'm about to get into. So asymmetric encryption has two things, and RSA, DSA, usually just use RSA, that's good enough. It tends to be actually better than DSA for some reasons due to key length. And so there are two goals for asymmetric encryption. You want to encrypt a message so that only one person can read it, and you also want to verify your authorship of something. So it encrypts basically this way. So instead of using the same key in the forward and the inverse, you use a public key to encrypt and a private key to decrypt. And how it really encrypts is crazy fucked up math. So what you do is you determine P and Q. These need to be prime numbers. Multiply them together to get N. N is called a modulus. Just pick an encryption exponent, have it fairly small, and have it have a low Hamming distance. 10001 in hex is often chosen. Also 3 is chosen sometimes. The decryption exponent is that, E inverse, modded with the Euler's quotient of N. Okay. And to encrypt something, you take your message M, you raise it to the exponent of the encryption exponent, and mod it with your N, and then you get C. And to decrypt, to get the message back, you take the ciphered text, raise it to the decryption exponent, mod it with N, and you get N back. I kind of strayed away from the capital letter, lowercase thing on the slide because this is kind of what the industry uses. But in general, N is public, E is public, D is very private, C is your public text that you send out to the world, and N is private. The problem is this only works for special values. So some of the requirements are M to the power of E needs to be greater than N. Because if you stare at that equation, M to the E mod N, if M to the E is less than N, the right-hand side doesn't really do anything. It doesn't apply the modulus once. So if you send out C, if M to the E is too small, An attacker can just take C, take the ETH root of it, and they get the message back. So you solve that with padding. Now you have a padding problem. You can't just throw random gibberish at the end of your message to make it bigger. That's not secure enough. So you need to use something like the optimal asymmetric encryption padding scheme, OAEP. Now that we've established that the message can't be too small, it also can't be too big. There's also the coppersmith attack, which basically says if you send the same message to multiple recipients using the same encryption exponent, an attacker would be able to combine those linearly and figure out the message really quite simply. So there's other crazy stuff too. You can't have P and Q, your initial prime numbers, to be too close to each other, otherwise they're easily factorable. P minus 1 and Q minus 1 shouldn't have only small prime factors. Wiener's attack happens when you have a small d. That's my favorite line in the presentation. There are timing attacks, so when you're doing all this modular arithmetic, if an attacker has a program running on the machine, they can detect, well, it took a really short amount of time to do this operation, so we can kind of figure, like, this happened, or it took long to do that, so it must be that. There's also just a whole range of these things called ciphertext and plaintext attacks. So you can have a chosen ciphertext attack, an adaptive chosen ciphertext attack, plaintext attack. It just goes on and on and on. You need to know what these things are if you're going to implement RSA. Going on, branch prediction analysis. If you see that the cache is getting missed, or you assume that an if statement will evaluate to true or false, then you can start learning things about what the actual algorithm is doing. There's quantum prime factorization. It's been proven that once we have quantum computers that are powerful enough, that we can solve the prime factorization problem in polynomial time. This is huge. No one's actually done it yet because it's really hard to make the qubits work together. So it's not a problem yet, but once we have computers that do that, anyone with enough money to buy one can just crack RSA. You shouldn't use a small n. That would be bad. So choose at least 2048. I would say just use 4096. So the moral of the story is don't implement this yourself. There are so many ways to attack this that you are going to fall into a pitfall. So the second topic for asymmetric encryption is verifying your authorship. So let's say Alice and Bob have the public keys of each other because they've exchanged previously. Alice wants to encrypt a message to send to Bob. So she encrypts M with his public key. She hashes the result of that and encrypts that resulting hash with her private key. And then she sends both the encrypted message and the hash off to Bob. Bob decrypts this hash with Alice's public key and verifies that the hashes match. And then Bob can decrypt the message with his private key. There are vulnerabilities behind this as well. Most of them are the same as what I explained earlier with asymmetric encryption. Also, you shouldn't be using the same public-private key pair for encryption as well as signing. Yes?
You mentioned just a second ago that the hash of the message is encrypted with Alice's private key?
Yes.
And decrypted with the public key?
Yes.
I thought that wasn't supposed to be possible.
It's really a one-way function. So if you take a chunk of text and then you run it through the algorithm with one exponent, the only way to get it back is with the other exponent. So in the traditional scheme, you would use the public key first, and it can only be decrypted with the private key. But you can instead encrypt something with the private key, and it can only be decrypted with the public key. You have to pad the hash, same as before, in case M is too small. Moving on, another place where you see signing is in certificates. And when you like to talk about how HTTPS is working, you usually say, oh, we're using SSL. It's not actually SSL, typically. Since 1999, you've probably been using TLS, Transport Layer Security. And the whole process behind that is enough for an entire talk. So I won't get into it. But the traditional way of SSL certificates and TLS certificates go is that there's this standard called X509. And it's very hierarchical. So you have these root certificate authorities, and they authorize, children certificate authorities, and then it's all in a tree. And so there's this chain of trust. If you're given a certificate, from eBay, let's say, you don't necessarily trust eBay. So you look at the certificate and say, oh, it's been signed by VeriSign. I trust VeriSign, so I must trust eBay. If you have Lion, there are about 175 certificate authorities already installed for you. Do you know those people? There's one from the Hong Kong post office. Did you know that? You implicitly trust them. I'm not saying that you shouldn't, but I don't know, maybe look into it. There's also poor revocation policies. You are capable of revoking a certificate. Let's say your private key got out. You are capable of sending out a message across the internet, basically, to these repositories of certificate revocation lists. But the browsers typically don't implement them very well because that would make the experience of browsing too slow. And also, certificates in the SSL scheme are commercially exploited. They have expiration dates on them, and the reason that they have expiration dates on them is twofold. One, because computers get fast, so you want them to expire before computers can hack them. And two, in case it gets out, in case your private key gets out, you want it to eventually expire so you don't have to keep telling people, no, don't trust that one, no, don't trust that one. And so once the expiration date goes past, you don't have to tell them that anymore. Commercial vendors, however, have decided that this is a great way to get money out of you. So the alternative is a web of trust model, which is used by OpenPGP. So a web of trust model uses a directed graph, which means that Alice can trust Bob. This is no different than X509 yet. It's also cyclic, so Alice can trust Bob, and Bob can trust Alice. And it's weighted. So Alice can kind of trust Bob. She knows Bob's an okay computer user, but she knows he's not the greatest. But Bob might think very highly of Alice, and so Bob places more trust into Alice, so that Bob will implicitly trust anyone that Alice trusts. But Alice would not trust anyone that Bob trusts. So that's kind of a cool feature. You don't need CAs in this particular instance, certificate authorities. It's just kind of a web. The way you get this started is with key signing parties, where people get together and say, oh, hi, I'm Brad. Here's my public key. Will you sign it, please? Kind of awkward. But would you like to see my ID? Which is a problem for me because I lost it on the way here. And there's also this high barrier to entry. Say you want to start doing this. Great. You don't trust anyone yet, so you can't actually send any messages, and nobody trusts you. So this is kind of a problem. So you just kind of have to say, I'm going to do this. I'm going to go to a bunch of key signing parties, which, by the way, don't really exist. And you're just kind of stuck without actually doing any of this. So how am I doing on time? Am I like way past already? No, I think I'm good. So Ruby implications. OpenSSL is built into Ruby. Awesome. So you can just do require OpenSSL. I included OpenSSL CIPHER module here just for brevity. So let's say I want to use AES-256 with a chain block cipher. Just create a new object. I tell it, okay, I want you to do encryption, generate and store a random initialization vector, generate and store a random key. I want to encrypt the characters foo bang, okay? And then call .final to apply the padding. And now you have a bunch of bits that are usually not printable, so you usually want a base 64 encode those. And then decryption is very similar. You create an object, you tell it, okay, you're going to do decryption, you tell it what the initialization vector is, the key, and then you update it with the crazy weird string that is generally not printable, and call that final, and you get foo bang back. And what about RSA? Again, pretty simple. You just call rsa.new 496, and wait a few seconds because it takes a while. And then let's say Alice gives Bob her public key. Then on Bob's side, he calls rsa.new with Alice's public key, generates this public key object, and then publicly encrypts foo and generates some encrypted blob. And then he can send that off to Alice. And then Alice can decrypt it by using her private key to create an RSA object and then doing a private decrypt on it. And all this padding stuff is automatically taken care of for you. OpenPGP. This is a problem in Ruby. Kevin Geesey gave a talk a year and a half ago, I think, at Windy City Rails, possibly, about how if you're going to write a library for Ruby or in open source, tell people if you haven't finished it yet. This is currently the shipped version of OpenPGP. I'll give you a hint. The decrypt method looks awfully similar. So this is a problem. So I'm running a gem called idkfa. I haven't finished it yet. But it comes from the cheat code in Doom, where it gives you all keys, firearms, and ammunition. I'm really concerned about the keys in this case. So the purpose is to allow the encrypted embedding of sensitive information like passwords or API keys into your code repository. And it's decryptable only by the authorized people or servers. So the anti-use case for idkfa is, okay, your app connects to a database. Big surprise. Okay, so that means you got to keep the database.yaml file out of the code repository, right? So you have to send out updates to that file via SCP or SneakerNet, and then boom, your deploy fails because you forgot to update the server. How many times has that happened to anyone before? Yeah. I'm just going to assume that none of you other people actually write Rails apps. So the use case for idkfa is that you check in database.yaml into your code repository, and it just has some ERB. And this idkfa method reads a file that's also checked into your code repository and decrypts it, assuming that you have the appropriate private key in your home directory. So you can grant access to other people to let them modify that file by using something like idkfa import and then take in their public key. You can update a server by saying idkfa Heroku setup or idkfa EY setup. And its status is it has a really nice README. It has some queues and some specs and some code, but not a whole lot. I wrote I'm doing a README-driven development on this, and I've basically finished the README, and then in doing research for this talk, I realized that it's not quite sufficient to be, because it's actually susceptible to a Coopersmith's or Coppersmith's attack. So I need to modify that a little bit. So currently it's unusable, and actually it has a very large image at the top of the README that says "Stop, don't use me." So actually take heed when you see that. So you've learned all about encryption. Where do you start? Okay, my unofficial requirements for you doing this, these are just suggestions. I'm not going to bring down the hammer on you if you don't do these. If you want to hack on idkfa, that is the cryptography part. If you're working on the CLI stuff, I'm sure all of you are capable. But if you're going to actually touch the cryptography part, you need to study for about 10 hours on just cryptography in general. If you want to start your own gem that does cryptography, do 30 hours of study. If you want to implement a mode, like CBC, but different somehow, spend 4 years analyzing this stuff. Go to all the cryptographic conferences. You need to learn a lot because what you do is probably not going to work the first time. If you want to implement an algorithm, another 4 years. If you want to design an algorithm, it's going to take 10 years of study to do that, to come up with it. And once you come up with that, you can't use it for 2 years because you need to have other people hammering on it. You need to put out a paper. You need to have people at a conference say, this is a great idea, or this is a terrible idea, these are the holes. So just assume that if you feel like designing the next AES, it's going to be 12 years before you're done. Also, while you're doing that, probably a good idea to get a PhD. And again, all these durations are revocable. Some of the greatest cryptographers out there who've been doing it for 30, 40, 50 years still make mistakes. So that just because you've spent all that time studying doesn't mean that you're capable of producing this bulletproof cipher. Also, you should start listening to Security Now. It's on the Twit network. These are some of the relevant episodes. Here are more of them. Total running time for all of those episodes is 17 hours and 23 minutes. Some of it is like ads. Some of it is like security roundups, like Windows had another patch today. But you should probably listen to all those before you start diving into some of this stuff. Basically, the idea I'm trying to get across is that encryption is really hard. So if you want to start doing it, start studying. Don't necessarily start doing. Read RFCs, read papers, go to conferences, etc. That's all I've got. You can get resources, credits, and everything from there. Thank you. Any questions?